There is a gas your body manufactures that you have never been told about. A gas, one atom of nitrogen bonded to one atom of oxygen, so simple in structure that it was classified as an industrial pollutant and a toxic component of car exhaust for decades. Chemists studied it as an environmental contaminant. Biologists assumed any molecule that simple and that reactive could only be destructive in living tissue. The discovery that the human body produces it deliberately, that the arterial lining manufactures it as its primary protective signal, was so unexpected that it earned 3 researchers the Nobel Prize in 1998. Nitric oxide, the molecule that tells the smooth muscle wrapped around every artery in your body to relax. When the muscle relaxes, the artery widens. When the artery widens, blood flows with less resistance. Pressure drops. Organs receive smooth, even flow instead of hydraulic hammering. The brain is protected. The kidneys filter without the pressure spikes that destroy their microscopic membranes. The heart pumps against a compliant system instead of rigid pipes. Without it, the arteries narrow. The pressure climbs. The smooth muscle that should be relaxing contracts and holds. The artery stiffens from the absence of the signal that was keeping it soft. The arterial lining itself manufactures nitric oxide, a finding that earned Furchtgott, Ignarro, and Murad the Nobel. The endothelium that medicine had dismissed as inert wallpaper for a century turned out to be a pharmaceutical factory producing the most important cardiovascular molecule in the body, on demand, from raw materials already circulating in the blood. Factory runs on one condition: it needs a signal to fire. Without a signal, the factory idles, and the consequence of idling is not neutral, it is catastrophic. Vascular smooth muscle contracts by default. This is the fact that makes nitric oxide essential rather than merely beneficial. Unlike skeletal muscle, which relaxes when unstimulated and contracts when activated, vascular smooth muscle maintains a tonic contraction in the absence of a relaxation signal. Calcium ions flow continuously into the smooth muscle cells through voltage-gated channels, driving contraction that narrows the artery. Remove the nitric oxide and the calcium channels reopen. The smooth muscle contracts. The artery narrows. Blood pressure rises. Because the relaxation signal stopped arriving. The artery is returning to its default state because the molecule that held it open is no longer being produced in sufficient quantity. Every artery in the body, coronary, cerebral, renal, femoral, mesenteric, depends on continuous nitric oxide delivery to stay dilated. The continuous delivery depends on continuous production. The continuous production depends on 6 daily inputs that modern life has systematically reduced. The lining sits quiet. The smooth muscle contracts by default. 6 signals trigger nitric oxide production through 6 different pathways. 6 separate discussions across different topics and different months described each pathway without naming the molecule they shared. The walking discussion described one pathway, the humming discussion described another. 4 other daily inputs: vascular compression, sustained muscle cycling, photochemical release from sunlight, and slow breathing, each triggering the same molecule through a different pathway. 6 different actions, 6 different physics stories, and every one of them was about one invisible gas arriving at one smooth muscle wall and delivering one instruction: relax the artery. The shear stress factory is the largest and best understood, and understanding how it works illuminates why all 6 factories matter. The shear stress pathway the walking discussion described activates endothelial nitric oxide synthase through glycocowitz bending. Blood flow across the endothelial surface generates frictional force that bends the sugar protein forest projecting from each cell, transmitting the mechanical signal to the nucleus. ENOS is embedded in specialized regions of the endothelial cell membrane called caveoli, small flask-shaped invaginations that concentrate the enzyme near the signaling molecules it needs. When the mechanical signal from the glycocalyx arrives, ENOS activates. The enzyme strips a nitrogen-oxygen group from the amino acid L-arginine, a raw material circulating freely in the blood, and releases nitric oxide as a dissolved gas into the surrounding tissue. The gas diffuses across the basement membrane into the smooth muscle layer. There it activates an enzyme called soluble guanylyl cyclase, which produces cyclic GMP, which dephosphorylates the myosin light chains in the smooth muscle cell, which releases the contraction. The artery relaxes. Flow produces bending, bending activates the enzyme produces the gas, and the gas relaxes the artery. Factory 1 is flow dependent. It runs when blood moves with force across the endothelial surface. It idles when you sit. The ENOS enzyme has a half-life of approximately 24 hours. If shear stress does not activate it for a sustained period, the cell downregulates its production. The factory does not merely idle. It dismantles. The cell reduces ENOS protein production, the cavilli that house the enzyme flatten, and the endothelial surface that was a pharmaceutical factory becomes a passive wall producing nothing. Flow-mediated dilation decreases measurably within days of reduced physical activity, reflecting reduced ENOS output from reduced shear stress input, as Green and colleagues documented in the Journal of Physiology. The factory responds to demand. Remove the demand and the factory scales down. Restore the demand. Resume walking. Resume movement. Resume the shear stress the endothelium was designed to receive, and the factory rebuilds. But the rebuilding takes longer than the dismantling. Days of inactivity produce measurable decline. Weeks of resumed activity are required to restore full ENOS expression. The asymmetry between decline speed and recovery speed means the person who alternates between sedentary weeks and active weekends is always operating below their ENOS capacity. The weekday decline outpaces the weekend recovery. Now, the nasal factory. Nitric oxide production from the paranasal sinuses, a source the vascular research had overlooked entirely, was measured by Lundberg and colleagues at the Karolinska Institute. The nasal NO pathway. The humming discussion described produces nitric oxide continuously from the sinus epithelium, independent of the endothelium, independent of ENOS, and delivers it to the lungs with each nasal inhalation, improving pulmonary vasodilation and ventilation perfusion matching. Factory 2 is vibration dependent. It runs when the sinuses oscillate with airflow, when the nasal passages carry the air that collects the gas from the sinus chambers, when the breathing route passes through the production site rather than around it. Mouth breathing bypasses it entirely. Sinus architecture evolved for this purpose. The maxillary, frontal, ethmoid, and sphenoid sinuses are hollow chambers lined with epithelium that produces nitric oxide at concentrations hundreds of times higher than the ambient air. The architecture is not accidental. The narrow ostia connecting each sinus to the nasal airway create the oscillatory flow pattern that maximizes gas exchange during nasal breathing. Air enters the sinus on inhalation, mixes with the NO-rich sinus atmosphere, and exits on exhalation, carrying the dissolved gas into the main nasal airway and down into the lungs. Humming amplifies the oscillation frequency, increasing the gas exchange rate by approximately 15-fold compared to quiet nasal breathing, which is why humming produces the measurable effects it does. Every hour spent breathing through the mouth is an hour the nasal factory produces gas that never reaches the lungs. The sinuses continue producing. The epithelial cells generate nitric oxide regardless of breathing route, but the gas remains trapped in the sinus cavities when the mouth is open and the nasal airflow velocity drops. The mouth bypasses the sinuses the way a highway bypass avoids a town center. The air arrives at the lungs through a route that skips the production site entirely. The person who mouth breathes for 8 hours of desk work eliminates 8 hours of pulmonary nitric oxide delivery, not because the factory stopped, but because the delivery route was abandoned. Reactive surge factory operates through ENOS, the identical enzyme as factory 1, but through a different stimulus. Reactive hyperemia, the blood surge that floods a vascular bed after compression is released, is the key stimulus. Compressing a capillary bed, clenching the toes, pressing the thigh against a chair, occluding blood flow through isometric contraction, temporarily blocks flow. When the compression releases, blood rushes back into the bed at a velocity that exceeds normal resting flow. The transient spike in shear stress activates ENOS at higher intensity than steady-state flow achieves. The warmth the viewer feels after releasing a toe clench is nitric oxide, mediated vasodilation from the shear stress surge. Factory 3 is compression dependent. It needs the squeeze and release cycle that prolonged sitting eliminates. The reactive hyperemia surge produces ENOS activation at an intensity normal resting flow cannot achieve. The shear stress during the post-occlusion surge reaches values 3 to 5 times higher than resting shear stress, a transient spike that activates ENOS maximally and produces a burst of nitric oxide that dilates the vascular bed beyond its resting diameter. The dilation is measurable. Flow-mediated dilation testing, the clinical gold standard for endothelial function, works by measuring exactly this response. Compress the brachial artery with a blood pressure cuff for 5 minutes. Release. Measure how much the artery dilates from the reactive hyperemia. The dilation measures the nitric oxide response. Poor dilation indicates poor ENOS function. The daily behavior that maintains this factor is simpler than the clinical test: shifting position, crossing legs, standing from sitting. Each position change compresses and releases a vascular bed, producing a small reactive hyperemia that activates factory 3. The person who shifts position every 30 minutes produces dozens of mini-cycles throughout the day. The person who sits motionless for 4 hours produces 0. Metabolic factory is the most recently discovered. Metabolic effects disproportionate to the Soleus' size, revealed by Hamilton's data in iScience, but the mechanism emphasized in that discussion was glucose clearance. What was not named sustained contraction-release cycling of the Soleus during seated heel raises maintains low-level shear stress in the calf vasculature. The blood does not stop flowing through the calf during sitting, but without Soleus contraction, the flow velocity drops below the threshold that activates ENOS. Sustained heel raises maintain just enough flow velocity to keep the enzyme producing. Factory 4 is contraction-dependent, the partial maintenance signal that prevents complete ENOS shutdown during seated hours. Hamilton measured the metabolic effects. What the measurement implied for nitric oxide was not stated in that paper but follows from the shear stress physics. Any blood flow velocity increase in a vascular bed activates ENOS in that bed. The Soleus contraction-release cycle during seated heel raises increases calf blood flow velocity above the resting seated threshold. The ENOS in the calf endothelium activates. The nitric oxide produced is local. It relaxes the calf vasculature, not the coronary arteries. But the local production contributes to the systemic nitric oxide pool and prevents the complete ENOS shutdown that 8 hours of motionless sitting would otherwise produce. Well, the photochemical factory is the one no prior discussion has reached. Human skin stores nitric oxide in chemical reservoirs, as Weller discovered at the University of Edinburgh, nitrite and S-nitrosothiol compounds distributed throughout the epidermis. These reservoirs are loaded through 2 pathways: dietary nitrate, concentrated in beetroot, leafy greens, and celery, is absorbed from the gut, circulates in the blood, and is converted to nitrite by bacteria on the tongue and in the oral cavity. The nitrite distributes throughout the body and concentrates in the skin. Endogenous nitric oxide production from the other 5 factories also contributes. Any excess NO that is not consumed by the smooth muscle is oxidized to nitrite and stored. The skin accumulates both sources over time, building a reservoir that sits dormant until activated by light. Reservoir capacity is substantial. Weller's measurements showed that a single session of whole-body UVA exposure releases enough nitric oxide from the skin to lower systolic blood pressure by several millimeters of mercury for 30 to 60 minutes, a pharmacologically meaningful dose from a pathway that requires no enzyme, no amino acid substrate, and no cardiovascular exercise. The factory is purely photochemical. Photon hits bond, bond breaks, gas releases. Trigger is light. UVA radiation, the longer wavelength ultraviolet that penetrates deeper into the skin than the UVB that produces sunburn, breaks the chemical bonds holding nitric oxide in its stored form. The gas releases from the skin into the local bloodstream, reaches the smooth muscle, and triggers vasodilation. Blood pressure drops, measurably, reproducibly, through a pathway completely independent of ENOS, independent of the endothelium, independent of exercise. Factory 5 is light-dependent. It runs when UVA photons hit bare skin. It is the production pathway that indoor living eliminated, and the pathway whose absence may contribute to the higher cardiovascular mortality observed at northern latitudes, where UVA exposure is lower for more months of the year. Weller's data carries an uncomfortable implication the viewer deserves to hear stated directly. Cardiovascular disease is the leading cause of death globally, responsible for approximately 18 million deaths per year. Melanoma, the most dangerous form of skin cancer, causes approximately 60,000 deaths per year globally. The ratio is 300 to 1. If moderate sun exposure reduces cardiovascular mortality by even a small percentage through the photochemical nitric oxide pathway, the number of lives saved from reduced heart disease and stroke may exceed the number of lives lost to increased melanoma risk. The data is preliminary, and honesty requires naming it as such. Prospective trials measuring all-cause mortality from controlled sun exposure have not been completed. But the direction of the evidence challenges the blanket sun avoidance message the viewer has absorbed for decades. The skin is not merely a cancer risk surface, it is a nitric oxide storage organ, the body's only light-activated pharmaceutical factory. The reservoirs of nitrite and S-nitrosothiol compounds in the epidermis evolved in an organism that spent its days outdoors under direct sunlight. The UVA wavelengths that release the stored nitric oxide penetrate clouds, penetrate light clothing, and arrive at the skin during all daylight hours and all seasons. The factory was designed to run continuously during waking hours. Indoor living shut it off entirely, and the cardiovascular consequences of that shutdown may be larger than the dermatological consequences of moderate exposure. Epidemiological data supports the direction. Cardiovascular mortality rises with latitude in a gradient that tracks UVA exposure more closely than it tracks temperature, diet, or healthcare spending. Carbon dioxide factory operates through a different molecular mechanism entirely. Carbon dioxide dissolved in blood directly relaxes vascular smooth muscle through pH-dependent pathways. The CO2 reacts with water to form carbonic acid, which dissociates into hydrogen ions and bicarbonate. The hydrogen ions directly affect the smooth muscle calcium channels, reducing the calcium influx that drives contraction. The relaxation is additive with nitric oxide. The two molecules produce combined vasodilation at a single smooth muscle wall through independent mechanisms. Slow breathing at 5 to 6 breaths per minute maintains higher arterial CO2 than rapid breathing, and the physics of Y is straightforward gas exchange. Each exhalation expels CO2 from the lungs. Each inhalation replaces it with ambient air containing almost no CO2. The faster the breathing rate, the more frequently the lungs are flushed, and the lower the arterial CO2 concentration drops. At 12 to 18 breaths per minute, the resting rate of most adults, the flushing rate exceeds the production rate, and arterial CO2 settles below the optimal vasodilatory range. At 5 to 6 breaths per minute, the flushing rate matches the production rate, and arterial CO2 stabilizes at the level where pH-dependent vasodilation operates most effectively. The factory requires no movement, no equipment, no special position, only a breathing rate slow enough to let the body retain the gas it is already producing. Factory 6 is breathing rate dependent. It runs when CO2 is maintained at optimal levels through slow nasal breathing. Chronic hyperventilation, the fast, shallow, mouth-dominated breathing pattern of stressed sedentary adults, depletes it. The evening I listed every protocol I had encountered: walking, humming, toe clenches, Soleus raises, sunlight, slow breathing, and traced each one back to the molecule it produced. The 6 separate recommendations collapsed into one pharmacological reality: 6 inputs, 1 output. Following one protocol supplied one factory. Following none left all 6 at idle. The molecule the arteries depend on was being manufactured through 6 independent pathways, and modern indoor sedentary life had reduced the input to every single one. Question shifts from how nitric oxide is produced to what happens when production falls below the threshold the arteries require. Because the decline is not simply a reduction in supply, the decline has a tipping point, and beyond the tipping point, the factory that was protecting the artery verses and begins destroying it. And then ENOS uncoupling. The primary nitric oxide factory requires a cofactor called tetrahydrobiopterin, abbreviated BH4, to function correctly. BH4 keeps the electron transfer chain within ENOS coupled. The electrons pass from the reductase domain through the oxygenase domain and are delivered to L-arginine, producing nitric oxide as the final product. The coupling is precise. Each electron must reach the correct acceptor in the correct sequence. BH4 maintains the structural alignment that keeps this transfer chain intact. When BH4 is depleted, through oxidative stress, through chronic inflammation, through the elevated blood glucose of insulin resistance, or through prolonged ENOS inactivity, the electron transfer chain uncouples. The electrons no longer reach L-arginine. They leak from the transfer chain at an earlier stage and are captured by molecular oxygen instead. The product is no longer nitric oxide. The product is superoxide, a reactive oxygen species with an unpaired electron that makes it chemically aggressive, attacking lipid membranes, oxidizing proteins, and damaging the DNA of the endothelial cells the enzyme is embedded in. Uncoupling is not a breakdown. The enzyme does not malfunction in the way a machine breaks. The enzyme functions perfectly. It accepts electrons, it transfers them through its domains, it produces a product, but the product has changed. The structural alignment that BH4 maintained, the precise positioning that directed electrons to L-arginine, is no longer held. The electrons follow the path of least resistance, which without BH4 leads to oxygen instead of arginine. The factory runs. The output reverses. ENOS uncoupling is not theoretical but measurable in human arterial tissue, as Fursterman and Munzel established in Circulation. Endothelial cells from patients with cardiovascular risk factors, diabetes, hypertension, hyperlipidemia, smoking history, showed higher superoxide production from ENOS than endothelial cells from age-matched healthy controls. The enzyme was present in both groups. The output differed. The healthy endothelium produced nitric oxide. The diseased endothelium produced superoxide from the same enzyme through an identical catalytic cycle with depleted BH4. Now, the superoxide produced by uncoupled ENOS reacts with any remaining nitric oxide in the vicinity to form peroxynitrite. This reaction occurs at near diffusion limited speed, faster than any enzymatic scavenging system can intercept. The peroxynitrite is more damaging than either superoxide or nitric oxide alone. It oxidizes BH4 directly, which depletes the cofactor further, which increases the uncoupling, which produces more superoxide, which creates more peroxynitrite, which oxidizes more BH4. The cycle is self-amplifying. Each turn of the cycle deepens the uncoupling. The factory that was protecting the artery has become the primary source of the oxidative damage that accelerates atherosclerotic plaque formation, endothelial dysfunction, and arterial stiffening. Reading Fursterman's paper on ENOS uncoupling, the six-factory model acquired a dimension I had not anticipated. The decline had a threshold, and beyond that threshold, the primary factory reversed its output from protective to destructive. The arithmetic is worth stating directly. The person who sits all day, breathes through their mouth, stays indoors and never compresses a vascular bed is not merely producing less nitric oxide. 5 of their 6 factories are idle. And their 6th factory, the endothelial ENOS that should be their primary source, may have uncoupled and begun producing the superoxide that accelerates the arterial damage the missing nitric oxide was supposed to prevent. Anyone with diagnosed cardiovascular disease, uncontrolled hypertension, or a history of blood clots should discuss the 6-input framework with their physician before implementing changes. The interactions between nitric oxide production, existing medication, particularly nitrate medications, and blood pressure regulation require medical oversight. Each factory requires a different input. Each input has been reduced by one lifestyle pattern, and the reductions are not partial. They are near total for most adults in the industrialized world. Shear stress reduced by sitting. The average office worker sits for 9 to 10 hours per day. During each seated hour, blood flow velocity in the femoral artery drops by approximately 30% compared to standing, and the shear stress that activates ENOS drops proportionally. Less walking means less endothelial, bending means less enzyme activation means less nitric oxide, nasal nitric oxide reduced by mouth breathing, screen posture, the forward head position, the drop jaw, the open mouth that accompanies hours of computer and phone use, converts nasal breathers into mouth breathers for the duration of the screen session. Reactive hyperemia, reduced by continuous sitting. No compression release cycles occur in a body that does not shift position, does not cross its legs, does not stand and sit, does not compress and release a vascular bed. The surge factory needs the squeeze needs movement, and movement needs a reason to stand. Soleus cycling, reduced by sitting without any lower leg movement. The metabolic engine idles. No heel raises, no ankle pumps, no sustained contraction. Release cycling to maintain even the trickle of shear stress that keeps the calf ENOS minimally active. Photochemical release, reduced by indoor living. UVA radiation cannot penetrate standard window glass. The silicon dioxide in glass absorbs ultraviolet wavelengths below approximately 380 nanometers. the exact wavelengths that break the bonds holding nitric oxide in its stored form. Visible light passes through, the warmth passes through. The wavelengths that release stored nitric oxide from the skin do not. The person sitting in a sunlit office feels warm and sees daylight but receives zero photochemical factory input. CO2 vasodilation, reduced by chronic hyperventilation. Stressed, sedentary breathing, fast, shallow, mouth-dominated, blows off carbon dioxide faster than the body produces it. Arterial CO2 drops. The pH-dependent vasodilation that CO2 provides diminishes. Factory 6 runs at reduced capacity for every hour of stressed breathing. The carbon dioxide factory is the only one of the 6 that operates through a non-ENOS mechanism. It does not require the endothelial enzyme, does not require shear stress, does not require physical movement. It requires only that the breathing rate stay slow enough to maintain arterial CO2 at the level where pH-dependent vasodilation operates effectively. The breathing rate mechanism already established determines whether Factory 6 runs or idles. And the factory that requires the least physical effort is paradoxically the factory most degraded by the psychological state of modern life, because stress drives respiratory rate upward, and elevated respiratory rate depletes the molecule the artery needs. 6 factories, 6 inputs, all 6 reduced by one behavioral pattern: indoor, seated, mouth breathing, stressed, still. The pattern is not exotic, it is the default mode of adult life in the industrialized world. The office worker, the commuter, the evening television viewer, the person who drives to work sits at a desk, drives home, and sits on a sofa. Each hour of this pattern reduces the input to every factory simultaneously. The reduction is not dramatic on any single day. It is cumulative across years and decades, the ENOS expression down-regulating slightly each month, the glycocalyx thinning from reduced shear, the BH4 cofactor depleting from rising oxidative stress, the skin nitric oxide stores draining without UVA replenishment. The artery receives less relaxation signal from every direction simultaneously, and the deficiency compounds across time in a way that simple addition cannot capture. Because the reduced nitric oxide from 5 idle factories increases the oxidative stress in the vascular wall, and the increased oxidative stress depletes the BH4 cofactor that keeps the 6th factory coupled. The 5-factory deficit drives the 6th factory toward uncoupling. The uncoupling produces superoxide that further increases oxidative stress. The increased oxidative stress further depletes BH4, the idle factories, and the uncoupled factory amplify each other. The deficit in one accelerates the reversal in the other. The decline is not 6 separate problems. It is one lifestyle producing 6 simultaneous deficits at one smooth muscle wall, and potentially converting the primary factory from protective to destructive through the uncoupling the cofactor depletion produces. These are not metaphorical factories. They are biochemically distinct production pathways, each catalyzed by a different mechanism, each requiring a different daily input, each producing the same molecule through a different molecular route. The shear stress factory and the reactive surge factory share the ENOS enzyme but require different stimuli. The nasal factory uses a completely independent enzyme system. The photochemical factory uses no enzyme at all, pure photochemistry releasing stored molecules from chemical bonds. The CO2 factory operates through pH chemistry without any nitric oxide production. It produces vasodilation through a parallel pathway that multiplies the effect of whatever nitric oxide the other 5 factories are generating. 1 nitrogen atom, 1 oxygen atom, molecular weight, 30 Daltons, lighter than a single amino acid, simpler than a sugar molecule, smaller than almost any pharmaceutical compound. Half-life approximately 5 seconds in biological tissue. The molecule degrades through reaction with hemoglobin, through oxidation, through combination with superoxide. The molecule degrades almost as fast as it is produced. Every artery in the body requires continuous replacement of a molecule that vanishes almost immediately after production. The smooth muscle is waiting, contracted by default, tightening the artery with every second the signal fails to arrive. It has been waiting since the last molecule degraded. 5 seconds, then it needs more.